Okay, so this is our last review session for the last quiz, the big quiz. This will be on chapters 5 and 6, which is basically series. But I listed here a couple of what you of course should do is look at all the material that I posted on these chapters 5 and 6. That's the advantage of these two chapters, is that you can go back and look at all the videos and look at all the homework solutions and quizzes and so on. That's something you couldn't do for the first part of the quiz. So there are some good advantages to online teaching, clearly. In particular, so look at all your quizzes, but I want to point out a couple of things where you particularly find a lot of review is, first of all, I did actually do a review already on series, but that was just not on power series, just a regular series, which is basically the two type of questions, the first two type of questions I will ask. So for those first two type of questions, just go look at this review lecture from session 23. You can also, for that, as a result, we had a quiz, the quiz 8, where I asked you to do 2 problems, but there are 2 other problems you haven't done, or perhaps you did, but go try those so that you can find some problems there too. There's also the departmental review sheet, which I do not really recommend because it's not full. It doesn't cover all the type of series that we've done, and also not the type that I will ask you. My own reviews are, and my own quizzes give much better idea of what to expect. But of course, you can use them for extra practice. And you might have gotten an email. I've also explained it briefly at the top of at the webpage, that there is this web work that the department has set up for people that want to try out these departmental finals. But this come from the departmental review sheet. Okay, so. I'm saying this is something you can do, but you don't have to do, and I just don't do that alone, right? You have to definitely look at all the reviews and lectures that we have, especially the reviews and the quizzes and the homework solutions, so make sure that you go over all this material. Okay, so I'll post this material, I'll post this also on the webpage, but I just wanted to tell it already here that you know what else there is. But so in this little video, I'm not going to make it too long, I'm going to talk about basically the 2 last questions. So the first 2 questions is about conversion of a series. That was basically what the quiz 8 was asking. And ACCC, this absolute convergence, conditional convergence. I remind you that remember that is basically 2 things, right? For the CC, you do the alternating series test. So CC, you do the alternating series test, and if this test passes, then you know you already CC, but then you have to do another test. So this will tell you whether you're CC or perhaps divergent, of course, and another test, which depends on the type of series, to find out whether it's AC or not. Well, okay, or not, or CC, okay? Okay, I explained this elsewhere, so I don't want to spend time on this too much now. So I want to go over the last 2, although there are also reviews for these last 2. There were quizzes on both of these, but just to have another review where everything is a little bit together. So I'll do a couple of 1 or 2 from each or something, probably only 1 of each. So first of all is about this power series, right? And then we one of the main things that we did with them was find the range of convergence and the interval of convergence. So let's work out an example. I'll take this one here, summation 3 to the n x plus 3 to the n divided by 6n plus 1, times n. Let me see, yeah, that's what I want to do. Okay. So step 1 was to find what in the book they call rho, to find the range of convergence, we had to calculate this limit, the ratio test. So this is the ratio test here. So the limit for n going to infinity. In the bottom we have the actual formula. And in top you get the same thing with 1, where you place n by n plus 1. So 3 to the n becomes 3 to the n plus 1. Well, that's nobody's problem with that. X plus 3 becomes x plus 3 to the power n plus 1. Now what is 6 to the n plus 1 become? Now if n is replaced by n plus 1 and then you have to add another 1, well, that means it's n plus 2. I hope that everybody sees that's what it is if you replace n by n plus 1 in here. right? This n is replaced by n plus 1, but there's a plus 1, so it's altogether n plus 2. And of course, then this is n plus 1. Okay, now there are absolute values, very important, because those absolute values are going to apply here to the x plus 3, because that could be negative. Also, we should determine the center, minus 3, right? Yeah, I'm solving this, but the best way to practice this is actually do it yourself and then look where you get stuck, or if not, hopefully not, then it's all fine, right? Then you can double check your work. Okay, so pause the video, try it for yourself. Okay, so limit n going infinity. Now put everything together. The 3n plus 1 goes there. The absolute value x plus 3. Please do not forget that. I know some of you are lazy and not write it, but I've seen most of you then at the end put it there back, but some of you don't, and then got completely confused. I got like half intervals or something, and nothing made sense anymore. Okay, so what else? This part is also going to come on top, 6n plus n, and n. Okay, and then in the bottom we're going to have a 3 to the n, an absolute value x plus 3 to the n, a 6 to the n plus 2, and an n plus 1. Now, there are the different types of functions here, right? These are exponential functions, powers, and we can always cancel them very easily, and that's why we align them. So, no, that's not what I want to do. So, let's see. So we cancel, then is 1, 3 left, right? Let's write it this way. The same here, and that's of course very important always with our x plus 1. See, this can never be in the denominator. This x plus 3 must always in the top. And normally it's power 1. It could be a different power, but normally it's power 1. And then the powers of 6, well, it's same thing. How do you cancel? Well, the biggest one is in the bottom, so let's write it in the bottom. Well, so you subtract this exponent. No, sorry. Yes, you subtract this exponent from this. So the result is this is gone, and this is just power 1. And therefore, there's just a 6. And this n over n plus 1 we wait with. Good. So now, what we have? Let's put out what we have. Go back in black. I have the 3, this 3. I have this 6. I have also the x plus 3, because it doesn't depend on n, so there's no reason to keep it inside the limit. And now I have this n over n plus 1. Now, this is a quick limit, but sometimes people think, whenever you see a fraction like that, you have to do it this way. No, if there's on top nothing, then and you plug in, if you have something like that, you put in infinity, and you see 1 over infinity is 0, right? The problem is, why are we doing it here and not in the previous case? Because if I plug in infinity, I get infinity of infinity. It's this indeterminate form that forces me to do something. Okay. So now we all know, hopefully, what this is. We divide top and bottom by the highest degree. So we get 3 over 6, x plus 3, and then this would be, okay, so this, okay, yeah, okay, I'll write it one more time. 1 over 1 plus 1 over n, and of course this limit is just 1. Okay, we get 3/6 x plus 3. Now, this is never the end of the story, because we're doing the ratio test. We have to put now this less than 1. Okay, and then we solve for this absolute value of x minus the center. Okay, we solve for that. So we bring, well, 3/6 we could have, why was I not simplifying, right? Okay, half. So bring this to the other side. We get x plus 3 is less than 2. And now we can solve this algebraically, or you can just, I find it easier to just do graphically. Say, okay, my center was at -3, right? I hope that everybody sees it's -3, not +3, right? Because it's x minus c. So to get the plus, we have to do minus minus. And now the 2 tells me I can go 2 this way, that brings me to -1, or 2 that way, that brings me to -5. Okay? So for now, we know for sure that inside we have conversions. So, oh, that's not, this is the one. So we have conversions here, but we don't know yet at the endpoint. Sorry, I was supposed to not touch the endpoints yet, but I did. Okay, so that's what remains. And please do this. You're going to lose points if you don't do this out. Last time I did the extra credit, but this time it will be part of the credit. So the interval of convergence. Yeah, I kind of lost the numbering of my steps, right? So this was, okay, so what was the radius of convergence here? The radius of convergence is 2, right? So let's call this step 2, where we figure out what the radius of convergence is and what we make the interval. So now, step 3, the interval of convergence, that means actually really the endpoints. And what do I mean with that? Well, here, these are the endpoints, right? And how do we do this? Well, there's only one way. That is, you take that endpoint and you plug it into that original series that we have there. So I put the -5 on top there, and so get summation 3 to the n. There was -5 plus 3, so it is -2 to the power n. In the bottom I have 6 to the n plus 1 and an n. Okay, what happens? Well, let's see. Always when I have a minus sign, a power of a minus sign, split this out. So make it 3 to the n times -1 to the n, 2 to the n. Okay, and then in the bottom we have 6n plus 1 n. Now 3n times 2n, a product of powers is the product is the power of the product. So it is 3 times 2 to the power n, so 6 to the power n. The -1 to the n, I always keep the -1 to n separate, because it is the sign. That's the only one that I keep separate. And then 6n plus 1, you see what happens is that these guys cancel, right? So, and again, we have a 6 left. And then, and the n. So we get 1/6 summation -1 to the power n over n. Now, what can we do here? Well, it's an alternating series, so we can do the alternating series test. Okay, so what we have to do, we have to take the limit for n going to infinity of this quantity, 1/6, 1 over n. The 1/6 was outside, but I put it back inside. And what is this? Well, now, as I said, right, this is not an indeterminate form. If I plug in infinity, you get 1 over infinity, which is 0. Now, that's what we want. So we have convergence here. So let's mark this here, so we get an inclusive point here. Whatever way you mark it or you write it as an interval, I don't make too much fuss out of that. Okay, now what about x equals, what was the other one? 2, no, -1. X is -1. Okay, we plug it in again. So now we're going to plug in here. We're going to plug in here -1, so this whole thing will be 2, right? Okay. So we get summation 3 to the n, 2 to the n, 6 to the n plus 1, n. It's basically, very often these calculations are very similar, but they're not the same, of course. 6n plus 1 n. The 6n and cancels out, we have a 6 left. So we have now 1/6 summation 1 over n. Now this you should recognize that this is the the harmonic series. The other one was the alternating harmonic series. If you tell me alternating harmonic series, I'm good too. But here you could either say this is the harmonic series, and we know this is divergent. Okay. Or alternative, you could say it's a p series. P is 1, and this also means divergent. Two ways of saying the same thing. So this would mean that we have let me get rid of these little circles here. And what it looks like is now we have an open here. So this is not included. Okay, that's it. Now you see that to do the endpoints, there's a little bit of work involved. So previously I put it as extra credit, and I sometimes feel that students think, oh, this is something smallish. So if I don't do it, it's fine. No, it's going to be half the points, right? Because it's almost, okay, this is work, but it is really just scratching things out. Here we have to think. You have to think what series I'm going to use, what test I'm going to use, and so on. Okay, so this is going to be half the points. So do not forget this part. Okay, all right. So they all are very similar. As I said, you can use the practice examples from the departmental review sheet or the one that I posted. So by all means. So but this is definitely something that is not on these review sheets, and this is the last type of question that I will ask is working with Taylor series. Okay, but I promise you I will help you. So for instance, the question would be this: find the first, and again, some of you actually solved the quizzes on this by writing the summations with the sigma sign, but I'm not going to ask you. It's enough to find the first I'll tell you how many non-zero terms. So here, find the first, and I'll be gentle, 3 non-zero terms. Now, I have seen people interpret this, up to degree 3, or up to degree 2 even. No. That's not what it will be. You'll see. Very often these degrees get very big here, but many, many other terms are zero. So you really have to find 3 non-zero terms. So it's different than degree 3. Okay, I hope you understand that. I think in this particular example, that would be actually nothing then. 3 non-zero terms of the following series. You take the integral of 15x plus 16x cubed times the arctangent. Where do I get those guys, huh? X cubed dx. Okay. And I might ask, and what is the radius of convergence? Many of the Taylor series that we work have infinite radius of convergence, but some do not. And actually here we won't. Okay, so now if I give it this just like that, you could try. So by all means, stop the video and try to figure it out. But I'll break it down in steps. So the first step is find a series. And again, first three non-zero terms. If you want to make sure that you don't forget anything, put 4 of those. But find a series for. Let's start with this guy, 1 plus x squared, using geometric series. So I'm even helping you here. Okay, I'm gonna give the hints as I work and then work them out. But on the test, the hints will all be given at the same time. Okay, but let's work it out as I'm giving the hints. So what does this mean? We know that we have this geometric series here is given by, let's do 4 terms, but just, okay. And this is for x less than 1. That's the geometric series. That's where we always start from. And what we now want to get is instead this series. So what do we have to substitute in x? So what do we have to replace? So if we make this x here into like a placeholder, what should I put in there? Well, I have to put in minus x squared, right? So I'm going to do therefore the same thing in here. Replace each of these x's by minus x squared. So get 1 plus minus x squared, I put in parentheses, plus minus x squared squared, plus minus x squared cubed, plus etc. for minus x squared less than 1. This also has to be worked out. Now let's do this first. That's actually easy because the minus that goes away. The square root of the absolute value is the same. And now we can take the square of an absolute value is the same. Now we take square roots and we get this. Okay, so the ratio of convergence has not changed. Okay, right. So this I wrote this as this way, but I could also have written as this way, right? But to calculate, you have to you use the inequality, and then you can make the conclusion again that r is still 1. Okay, let's write this out a little bit neater. 1 minus x squared, then. Please, a power of a power, it's multiplying exponents. Don't make this mistake, because then you get really sometimes weird things. Oh, plus it's a third degree, right? So there's going to be a negative here. X to the 4th minus x to the 6th, etc. Okay, that was the hint 1. So hint 2 would be use 1 plus and the derivatives to find series for arctangent. Now, this is something that you have to know. Why is this working? Because the antiderivative of 1 plus x squared dx is arctangent. I write it here. Okay, so that's the thing that you need to know then. Hopefully you know, right? These are still calc 1, but no, there's actually calc 2. So, okay. But we have a series, we just did that. It is 1 minus x squared plus x to the 4th minus x to the 6th dx. Now, and the deriving, that is power by power, x minus x cubed over 3 plus x to the 5th over 5. Okay, I'll do one more time, but I don't think I need it. Now, what happens to the ratio of convergence? Nothing. Integrating or taking derivatives does not change it. Okay. 3. Next hint. Use 2, the one that we just found, to get a series arctangent x cube. Why? Well, because that's what we had here, okay? All right, so what does that mean? Well, how do we get from arctangent x to arctangent x cubed? Not by integrating, by substitution, right? So that we have three techniques always, right? Substitution, well, no, there are four techniques, I said, sorry. Substitution, integration, derivatives, and multiplication. Okay, so here we have to substitute. So that means I'm going to replace, again, let's do this in purple here. So this x here will become x cubed, and then this axis will become all x cubes, right? I'm going to write it here. Arctangent x cubed is x cubed minus x cubed to the power 3. Take your time to work this out. Plus x cubed to the power 5 over 5. And I'm going to stop with these three terms because we said three terms, right? What is this? Well, that's x cubed minus x to the 9th over 3 plus x to the 15th over 5. Multiplying exponents, right? Not x to the 8th, the last one. Huh? Okay. What happens to the radius of convergence? Well, nothing, because we just... oh, no, no, sorry. Well, it actually nothing happens, but I should check this. Sorry. So, let's see. The previous one here, this was for x less than 1. Now we have, whenever you substitute, your radius of convergence can change. Of course, if it's infinity, it's never going to change. But if it's something finite, then it can change. Let's see. X cubed less than 1, but it's the same as x cubed less than 1. And kick the cube roots, x less than 1. So again, nothing has actually changed. Sorry, but there's a little argument that's needed here. Okay, step 4. We're almost getting there. Use 3, so what you just did, to find series for the product now. The product was, let me see, 15x plus 6x cubed. 15x plus 60x cubed. Actually, I've seen somebody do this, and let me try this. Huh. Okay, and so now what? What do we do now? Copy. And then hopefully I can do paste here. Let's see. Paste. There we go. See how neat. That could have been helpful if I found this a little bit earlier, but okay, here we go. So how to find a series for this guy? Well, it's a multiplication. So let's see. We have 15x plus 60x cubed. We're going to multiply this with x cubed minus x to the 9th over 3 plus x to the 15th over 5 and so on. We look at the terms. I always do the table one, and you might be used to that, but sometimes when it's a smaller, some of you got a little bit confused because this thing, they were questioning whether it's a series, but any polynomial is a series. A series is, we say, is a polynomial of infinite degree, but of course, polynomials of finite degrees are also series. They are just very easy series, okay? So what you can also do is work this out, distribute this. So let me show you, just to show you a different way. Well, I hope that doesn't confuse you. So we're going to multiply this here, so we get 15x to the 4th minus 15, now I'm going to multiply these two, that is 5x to the 10. Right, 15 divided by 3, and then we always add x. Now we're multiplying, so we're adding exponents, right? And then the last one is plus 3 times x 16, right? This one times this one. Okay, the 15 over 5 that cancels. Plus dot dot dot. Now, it don't make two series of this. Now you're gonna take this one and you're gonna put it underneath here, because you're gonna add this also here. So, sorry. I'll do this in different color. Let's take this one and multiply that. So we're going to distribute this now. Okay? But I'm going to write it here. So that is 60x to the 6th minus 60 divided by 3 is 20x to the 12th. And then 16 divided by 4 is 14x to the 18th plus dot dot dot. Now if I ask the first 4 non-zero terms, that means the first 4 But be careful, sometimes you can have like terms. In this case, actually, there were no like terms, but normally there are like terms. So you have to first put them together and then look for the first 3 non-zero degrees. So here, of course, the first 3 non-zero degrees would be, I'll do it in green, the 4th degree, the 6th degree, and the 10th degree. Okay, so the answer would have been 15 x to the 4th plus 60 x to the 6th minus 5 x to the 10th plus. When you do the dot dot notation, you have to write things in ascending order, increasing order. Okay, so that's 4, and then finally 5. Use the series that you have now found in 4 to solve. That means we have to now find the integral of this thing. So the integral, can I still do the copy thingy? The paste, yeah, look at that. Dx. Now we found what this was. This is the previous thing, 15x to the 4th plus 60x to the 6th minus 5x to the 10th plus dot 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 dx, and the deriving. Oh, sorry, I should have mentioned this. What happens to the radius of convergence here? When you multiply, especially with a polynomial, nothing changes. To be really true, what happens if you would multiply, I'm just saying it for information, if you multiply 2 series, then the product will have the smallest of the 2 radius of convergence. Okay, but of course polynomials always have infinite radius of convergence because they are polynomials. You can plug in whatever you want in the polynomial. So this would have radius of convergence infinity. This one we know has convergence 1, we calculated that. So the smallest one is 1, so that's why this has radius convergence of 1. And now we enter derive, so again nothing will change, and so what the final answer here would be 15x to the 5th over 5 plus 60x to the 7 over 7 minus 5x to 11 over 11 plus dot 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 plus c. And that's it, that was the answer. So I always will have these guidelines that you can use here, 1, 2, 3, 4, but of course it is cumulative. That means if you make a if you get stuck early on, then you're really in bad shape. Okay, so I never take too difficult things, so you should be able to do this. We have done this now several times about arctangent. We have done it for ln x. Sometimes when it comes to sine and cosine and ex, we have the tables. We can use those. You don't have to do anything. You can just use the tables, right? So I remind you, we have that ex is 1 plus x squared over 2 factorial plus x cubed plus over 3 factorial plus so, and here the radius of convergence is infinity. For sine x, it is x, minus x cubed over 3 factorial plus x to the 5th over 5 factorial, dot dot dot. And cosine x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, etc. And all these have radius of convergence infinity. So those you can just use as is. Okay? All right, so this is the review. But don't just do this review, right? There's much more you have to do. Look back at all the videos and reviews, at least, especially of the other material.